Hello everyone, this is Shalaby, Amr Walid Shalaby. I am an electronics engineer from Cairo, Egypt, and this is my academic video resume to showcase my background and my aspirations for next academic steps. In this presentation, I'm going to first showcase my educational background. I'm going to describe my undergraduate research experience along with my graduate research contributions. I am going also to go through my skills and self-development journey, and finally I am going to conclude with my research interests and future aspirations. First of all, regarding my educational background, I hold a degree of bachelor's in electrical engineering from Zagazig University, Egypt. Graduated 2014. My specialization is in electronics and communication engineering, and my graduation project holds the design of a simplified RISC processor using Verilog hardware description language and was implemented on an FPGA board. Secondly, my graduate studies during my master's, I got a degree of Masters of Science from Cairo University, 2024. Specialized in advanced materials and nanomaterials, and my research in masters focused on the use of quantum dots in enhancing the conversion efficiency of solar cells. During my undergrad studies, I participated in some curricular activities. The most noticeable one is the implementation of a train monitoring system in which when a train passes through a beam, a barrier would lower down to prevent pedestrians and cars from crossing the crossing. And it was during an engineering control course, so the focus was on the control mechanism. Secondly, and during my graduation project, I led my team in the design process of a RISC microprocessor and implemented it on a Spartan 3E FPGA prototyping board. Also, I participated in summer internships, as we call them in Egypt, because all of them take place during summer vacation. I joined North Sinai Petroleum Company, NOSPCO, also Banha Electronics Company, and Rashid Petroleum Company, all of which was in the summer of 2011, 12, and 13, respectively. Also, during my undergrad era, I skilled and expertise in MATLAB, JavaScript, Java Basic, and Visual Basic, and Java, all of which I have to say was a very introductory experience, very introductory expertise. I didn't participate, I didn't get a profound experience in any of which until my graduate studies, where I used MATLAB in a very profound way. I will come to that later. Also, I gained significant experience in teamwork during undergraduate, either as a team member or a team leader in the previous two projects that I mentioned. Also, most of these skills were gained by self-learning, including Verilog hardware description language and actually VHDL also, but I focused on Verilog. And this trend actually continued with me until postgraduate studies. I continued using self-learning as a main learning mechanism for myself, even in postgraduate era. Also, I participated in many charity events, either with my colleagues to help my other colleagues find learning materials and books and so on, or by helping the poor in my neighborhood. Both I took place during my undergraduate studies. And in the graduate studies in my master's, Actually, I focused more on the research of quantum dot intermediate band solar cells. The main goal of such technology is to introduce an intermediate band in the band gap of the main matrix solar cell semiconductor. This is to use the sub-band gap photons to generate more photocurrent and eventually enhance the conversion efficiency, because these sub-band gap photons usually come across unabsorbed. So we want our research mainly focus on doing that, on making use of these unabsorbed photons. First, we started our research with focusing on the main drawbacks of indium arsenide, gallium arsenide quantum dot intermediate band solar cells, in which indium arsenide quantum dots were embedded in the intrinsic region of gallium arsenide solar cells. This technology, as we can see in this reference, which is Christopher Bailey's doctorate thesis, we can see that actually efficiency drop usually accompany such technology, and it first starts with dropping conversion efficiency, and we can start seeing an enhancement in conversion efficiency in very large quantum dot numbers. And here by quantum dots we mean quantum dot layers, layers of quantum dots. Also we can see in this JV curve that after 10 periods of quantum dots we see a drop, after 20 periods further drop, which actually was attributed to a fabrication fault. However, we cannot see a conversion efficiency enhancement until we reach 40 periods or 40 layers of quantum dots. Our research in this period focused on understanding and analyzing these systems and understanding why this conversion efficiency drop happens. Our study, and also not our only, but according to other references, refer to this drop because of the low conduction band barrier between indium arsenide quantum dots and the main gallium arsenide matrix, which leads to thermal escape of electrons. This thermal escape of electrons, or as it is usually called, coupling between the intermediate band and conduction band, leads to a drop in quasi-Fermi level separation, which also leads to the open circuit drop because it is directly related and directly proportional to the quasi-Fermi level separation. Second reason of this drop is the type 1 band alignment that indium arsenide quantum dots in a gallium arsenide matrix possess. Type 1 band alignment causes such high recombination rates and also causes this drop, this efficiency drop. The third reason is the high lattice mismatch between indium arsenide and gallium arsenide, which is 7.16 or above 7% between them. This causes problematic structured growth, also causes a low carrier separation efficiency and low carrier extraction efficiency, because quantum dots actually usually get captured inside the quantum dots during transport. So this excuse me, these three reasons mainly participate in the efficiency drop of indium arsenide quantum dots, indium arsenide, gallium arsenide quantum dot solar cells. Also, we can see this more vividly in quantum efficiency figures, where despite there is a vivid absorption, sub-band gap absorption that exists by adding quantum dots, actually we can see a clear drop in the quantum efficiency for above band gap photons. And this is mainly caused by poor carrier separation efficiency that's caused by the lattice mismatch. Our first candidate to overcome these drawbacks is the system of indium phosphide quantum dots embedded in the intrinsic region of an indium gallium phosphide solar cell. Indium gallium phosphide solar cell presents itself as a good candidate because of the wider band gap. This causes a higher barrier thickness or height between indium phosphide and indium arsenide, which we can see here. The higher barrier, yes, we are still in 200 milli electron volts. However, it is still higher than the 220 milli electron volt of indium arsenide gallium arsenide barrier. This higher barrier would eventually mitigate the V open circuit drop. This is the first point. The second point is that for larger indium phosphide quantum dots in indium gallium phosphide matrix, it has been proving that indium phosphide quantum dots possess a type 2 band alignment, or what I called a quasi type 2 band alignment, because eventually holes get confined along the edges of quantum dot, while electrons confined in the middle of quantum dot, which decrease somewhat the spatial overlap between the electron and hole wave functions, which we'll see later. This eventually will decrease recombination rates inside the quantum dots. Finally, the lower lattice mismatch between indium phosphide and indium gallium phosphide, which is 3.8, approximately 3.8%, which would eventually lead to a better carrier separation and extraction efficiency. This will lead also to better growth conditions, better or the ability to grow larger and bigger quantum dots while maintaining considerable and a good lattice quality. This we can see in wave function profiles of both indium arsenide, gallium arsenide, and indium phosphide, indium gallium phosphide systems. So, according to our simulations, indium arsenide, gallium arsenide system would have a very strict overlap. Excuse me. A very strict overlap of electron and hole wave functions on top of each other. However, this would cause a very elevated recombination rate, because, as we may know, that most recombination rate equations contain the product of NP. So at each point inside the quantum dots, the product NP would be the maximum level, the maximum a maximum value, which would cause to an elevated recombination rate. However, in indium phosphide, indium gallium phosphide system, as we said, the holes would be more confined towards the edges of the quantum dots. However, electrons would not be that confined. This would cause this clear spatial separation between hole and electron wave function profiles, as can be seen in this figure. This would cause the MP product, eventually recombination rate, to be not as maximum as the condition in the in indium arsenide, gallium arsenide solar cell or quantum dot solar cell. This is the first condition. The second condition, or the second thing, is that we implemented this system in a dual junction configuration, because indium gallium phosphide alone has a very large band gap, which results in a very low current. So it is not this feasible alone. So it is better implemented in a dual junction solar cell. So implemented it in a structure with gallium arsenide junction. So I just want to point again that quantum dot layers, which we will mention again in next slides, we mean the horizontal layers that usually should contain uniform quantum dot distribution. This is the first thing. The second thing, we simulated a whole stripe of quantum dots, and we assumed we forced or defined boundary conditions, periodic boundary conditions along the x-axis. So this strip should be, in case it should be repeated, it will give the same results. Our implementation was for quantum dots in the intrinsic region of the indium gallium phosphide junction, and knowing that the indium gallium phosphide junction is the current limiting junction in the dual junction solar cell, it should also enhancing this current should also enhance the overall current of the solar cell. This second point. However, damaging or decreasing or causing the decrease of V open circuit, yes, it would decrease the whole V open circuit of solar cell. However, because it is a dual junction solar cell, this decrease would be somehow minimal, and we will try to make it minimal by using this structure. By doing an external quantum efficiency study, we also found that many of our postulates came true. The first one is the better carrier separation and extraction efficiency that we assumed by using better material quality of indium gallium phosphide, which has a lower lattice mismatch. This led to a better carrier extraction available or very visible in high energy portions of our external quantum efficiency figure. This is the first point. The second point is that also we have vivid subband gap absorption at higher wavelengths or lower energies. This led to a very interesting profile of values. So at introducing or when we introduced the first quantum dot layer, we noticed a very large drop of V open circuit. We understood or we explained that this considerable drop in V open circuit was caused by the decreased optimization of dual junction structure. As we also know that dual junction structures or multiple junction structures generally are highly optimized structures. So changing the thickness or adding new materials would actually tip off this high optimized status, which we explained this drop by. However, by increasing quantum dot layer numbers, we noticed there is a continuous V open circuit drop. However, this drop is controlled, is managed, is not this severe compared to the other systems like indium arsenide, gallium arsenide solar cells. Finally, we noticed that the enhancement in current along with enhancement of efficiency was limited by the gallium arsenide junctions J short circuit. This is because actually increasing the indium phosphide content and increasing the absorbed portion of solar spectrum would lead to a decrease in J short circuit in the gallium arsenide junction. Eventually, after 3 periods of quantum dots, the decrease in the J short circuit of gallium arsenide junction would eventually make it the current limiting junction, which after this causes this drop in J short circuit and in efficiency. We can see it in the next slide here, because increasing the addition of quantum dots, yes, increased J short circuit of the indium gallium phosphide junction. However, by adding indium phosphide content to the upper portion of the cell, to the upper junction, the lower junction, which is the gallium arsenide junction, continues dropping J short circuit, which eventually after 3 periods make the overall make the gallium arsenide junction the current limiting junction and limits the overall current of the solar cell. When we compare the results of the indium gallium phosphide structure and the results of indium arsenide gallium arsenide structure, we notice that immediately after adding indium phosphide quantum dots, we notice an enhancement in conversion efficiency until we reach 3 quantum dot, this tipping point or this limiting point, and and then we start dropping again. However, we notice as somehow the opposite direction of enhancement in indium arsenide, gallium arsenide solar cells. In indium arsenide solar cells, by adding quantum dots to the cell, we immediately start seeing a drop in this in conversion efficiency, which is actually enhanced gradually until we start seeing some conversion efficiency enhancement, as we have seen in Christopher Bailey's dissertation, and here also we can prove that. So indium phosphide, indium gallium phosphide can reach considerable efficiency improvement by using much lower count of quantum dot layers or quantum dot periods. This is a very important thing to do or to notice. Also, we want to notice that maybe because we didn't add any amendments or any enhancements to the gallium arsenide junction, we got limited only at 3 quantum dot layers. However, we believe that if such attention was paid to the gallium arsenide junction, also an enhancement can be reached beyond this 3 quantum dot mark. However, our research was not directed to the optimization of a dual junction solar cell. It was directed more to the use of quantum dots, but future works can focus on that later. During this research journey, my skills and skill sets significantly enhanced. First of all, my MATLAB skills, which actually worked and had a crucial role in my research. I started undergrad knowing MATLAB as as a course during my undergraduate studies. However, in my master's studies, MATLAB was a cornerstone of my research, because first I would simulate indium phosphide, indium gallium phosphide structure using Silvaco TCAD. Then I would use these results to calculate the input spectrum to the gallium arsenide junction using MATLAB. Then I would take this spectrum, adapt it to and insert it again to Silvaco TCAD to simulate the performance of this gallium arsenide junction, and then take the performance of both the junctions and input it to MATLAB to calculate the overall curve. So this is actually only one step or one process that I used MATLAB in. Also, I used MATLAB in more things like the visualization of this data. All these figures that I showed earlier was shown in MATLAB. Also, the analysis of my data. Actually, personally, sometimes I used MATLAB personally to visualize something or to do some calculations in my personal life. So MATLAB, I had a very good MATLAB, and I usually call that MATLAB is the best friend of an engineer. Second of all, also my TCAD experience. I got accustomed and I got introduced to many TCAD tools. Also, Silvaco TCAD is my number one tool that I used during my quantum dot simulation and my quantum dot journey. Also, I used Numerical, but it was an introductory usage during the process of deciding which tool to use. But I eventually went with Silvaco TCAD. Also, I used COMSOL in a MEMS graduation project during masters and during the coursework period of my masters, in which I used it to simulate a microvalve that I took from a paper that studied this valve that should be implemented in a lab chip on a Mars rover. However, I used COMSOL to simulate this microvalve, which should be opened and closed electromagnetically. So I used COMSOL to simulate the deformation of the valve and the flow rate and flow speed and flow pressure inside the valve while closed and while opened. Also, I got accustomed to many programming languages. However, they somehow didn't make it to my master's research, but it was general learning using embedded C, which I took a very long term in it. Also Python and Visual Basic Application in Excel. I have introductory level of knowledge in them. However, I am open to learning and to expanding in them also. All these skills, I mean all of them, were learned by self-learning, by taking courses online, by reading online, by trying with my hands, by trying code by myself. So it is actually a motto for myself that self-learning actually built a large sum of my skill sets. Finally, my research interests. Actually, I am open to a range of skills, a range of research points and research interests. First of all, I am interested in exploring further applications of nano and quantum devices in enhancing the efficiency of solar cells. Also, I am excited to get accustomed to new devices. So I want to go outside of solar cells and generalizing my work to any electronic device. Also, I'm interested in things like single electron transistors, tunneling FETs, and other low power electronics. Also, I want to further explore the properties of nano and quantum devices and charge carrier interactions and behavior with them. Also, as you may have noticed, that my skill set until now is mainly focused on simulations and numerical simulations and theoretical stuff. My research interest in the future, I want actually to get more in depth regarding experimental work. I want more experimental work. I want more fabrication work. I want to go to a clean room, get physical samples, physical cells, get a fabrication experience with many fabrication methods. So this is actually a very important research interest for me in the future. Also, I'm open to returning to digital design using hardware description languages or FPGA prototyping boards. This is also an open thing for me. I don't shy away from that. Thank you very much for listening till this part. These are my contact details. I will also upload a copy of this video on my website. And these are my emails, my personal email and my academic email. Thank you very much. This is Amr. Thank you very much.